All right, in this problem we're asked to find the electric field within a uniform charge distribution. Now this charge distribution has spherical symmetry, but it's a spherical shell, so it has an outer spherical radius and a hollow spherical interior. So in order to get a little bit better idea of what's going on, let's go ahead and sketch that. So here's the hollow volume, 15 centimeters here. Here's the outer part of the shell, 20 centimeters. And basically this entire region here is filled with charge. We're asked to find the electric field a distance of 17 centimeters from the center. Because of the spherical symmetry, we're going to go ahead and use Gauss's law in order to do that. So I'm going to put a spherical Gaussian surface at a distance of 17 centimeters away from the center. Let's go ahead and calculate the flux through the surface in terms of the electric field strength E. Now the electric field is always equal to E dot dA, but because of the high spherical symmetry here, we know things about E. It must point outward from the center, and it can't depend upon the position. It can only depend upon the radius, so it can't depend upon the orientation at all. We talked about this in class quite a bit. The end result of these considerations is that the electric field flux is just the value of the E field times 4 pi r squared, where r is the radius of the Gaussian surface. In order to solve for E, we have to equate this E times 4 pi r squared to a charge enclosed over a constant epsilon naught. So how do we compute the charge enclosed? Well, we know that there's uniform charge density rho throughout the sphere. So if we know the volume of charge, since we know the charge per unit volume, we can figure out what the total charge enclosed is. Okay, so let's take a look. We know that the volume that's enclosed by the Gaussian surface itself is 4 pi over 3 r cubed. That tells you the total amount of volume that's enclosed by the Gaussian surface. Not all that volume has charge in it, though. There's a hollow center. So in order to get the volume of charge that's actually enclosed, we have to subtract out the volume center. This gives us the volume of the shell between its inner radius and the Gaussian surface. We can see now that we can actually solve for the electric field. E times 4 pi r squared. This r is the radius associated with the Gaussian surface. Notice it was specified in centimeters, but in order to be consistent with units, we'll convert it to meters to always be working in kilogram meter second units. Now there's a charge density of 5 times 10 to the minus 6 coulombs per cubic meter times a constant 8.85 times 10 to the minus 12 coulombs squared per Newton meter. So that's the rho over epsilon naught. Now, the next thing we need to include is the volume terms. 4/3 pi times the Gaussian surface radius in meters cubed minus 4/3 pi times the interior surface in meters cubed gives us the volume of where there's actually charge present. I see now that I can solve this for E. If I do a little bit of manipulation, I find that the electric field is 10,000 newtons per coulomb.